So welcome to Fusion EP Talks, a student-led webinar on fusion science and engineering physics. And today I'm pleased to welcome Professor Geert Verdoolaege, who will be giving a talk on data science and machine learning in fusion, foundations and applications. Professor Verdoolaege is a full-time associate professor in the Department of Applied Physics in Ghent University in Belgium, where he heads the research unit nuclear fusion. And for more than 15 years, he has been working on development on data analysis techniques using methods from probability theory, machine learning, and information geometry, and their application to nuclear fusion experiments. Professor Verdoolaege participates in ITP topical groups on diagnostics, as well as transport and confinement. He is a member of General Assembly of the European Fusion Education Network, FuseNet, and participates in scientific committees of several conferences on nuclear fusion and information science. So today's talk is a great opportunity for us to gain insight in the combination of the two most challenging issues in our time, which is fusion research and data science. Professor Verdoolaege, please welcome to start.
Okay, thank you very much, Katja. Thank you very much also to Fusion EP and Fusion EP alumni for organizing this. So it's actually an honor to be the first lecturer who gives one of these talks. As you know, Ghent University has been involved in Fusion EP since the very start, starting with Professor Geert Verdoolaege. And we have been continuing this over several years. Perhaps you also know, just as a little novelty, that the coordination of Fusion EP is no longer with our university in Ghent. It's now at one of our other partners, Aix-Marseille University, close to Cadarache. So that's, of course, an opportunity in France. And we of course, have all the trust that they will continue this, this important fusion education program into the future, which, by the way, starting from next academic year onwards, will again be funded with new grants. Of course, that is under the assumption that by that time, our situation, the health situation, will have normalized a little bit all over the world. Okay, so I'm going to give you an overview of what we do at the Department of Applied Physics at Ghent University in Belgium. As far as data science and machine learning is concerned, with, of course, applications in fusion. And I will briefly talk about some of the foundations, some of the mathematical and data science tools which we use to address data analysis problems in fusion. And then I will mention a number of applications that we are working on. Right. So this is an overview of the talk. We'll talk about data science, the history, some perspectives, the basics. So the foundation, some of the foundations of probability and building upon that, machine learning. And then these are the applications that I will briefly discuss, the main applications that we are currently working on. And then with some conclusions and outlook, I will end. Okay, so very briefly about data science. And taking a step back to get a bit of an overview of science, one could discern important trends. So until about 1,000 years ago, most of science, all of science actually was experimental. It was all based on observation, the experiment. And really only the last few 100 years, there is order of magnitude, there is the tendency to formulate hypotheses based on theoretical considerations and test these hypotheses by, again, referring to the experiment. Then, of course, came the age of computers, and only really about the last few decades, computational science became very important also, obviously also in fusion. And taking that one step further, one could say that more recently, of course, we have been doing data analysis for hundreds and thousands of years in a certain sense, but just more recently, the last 10, 20 years, this science has become more data intensive. And that is not only because of the amounts of data that have become available and the computational power that has become available, but also due to the complexity of the data and to relate those data to underlying understanding of the system that you are studying. And it's these days all over the science news, one could say that we are experiencing a data deluge, the era of big data. And I'm starting with that aspect of data science because it's the one that we are being confronted with the most, and because of course it's also one of the important motivations to do data science, just the sheer amounts of data coming from, for instance, high throughput scientific experiments like telescopes, particle accelerators, and also fusion devices. Scientific modeling produces also a lot of modeling data. And then sociology surveys in sociology, healthcare, of course, and monitoring of health, genomics, and remote sensing, Earth observation. These are some other areas of science that produce really a lot of data. And then, of course, most recently, I would say, are the data coming from media, from social networks, and then even looking towards the future, the Internet of Things, where all devices become, even simple devices become mutually connected and start producing a lot of data that some of which could be interesting, most of which is probably has to be filtered out. Okay, still talking about that movement towards a new era in science, if you want to put it with perhaps a little bit of exaggeration. There is even this book by Microsoft Research about the fourth paradigm in science that also takes that idea that we are now in a new era of data-intensive scientific discovery. Maybe you have also heard about Industry 4.0, where again that same idea percolates, where again, like Internet of Things, machines in a production line are connected, mostly wirelessly. And by doing that, they can collaborate. They produce, of course, in doing that, a lot of data. And again, this data has to be transferred and processed. Now, what I want to say in addition is that the amount of data is not the only motivation for doing good well-founded data analysis. There is also the aspect of data and model uncertainty. So we know that data are always measured with, well, if you do the measurement again, then usually you will get a slightly different number. So there is some what we could call statistical uncertainty. There is also uncertainty in the model that we often use to describe the data, to extract useful patterns from the data, because that is eventually what we want to do, to extract useful information from those data. And that uncertainty we have to take into account. Probability theory is, of course, the standard tool, although there are various flavors of probability. but the standard rule to address and quantify uncertainty. And secondly, there can be very complex and nonlinear interdependencies between variables, because one aspect of the physical system that you're interested in is influenced by a lot of other variables, as is often the case in a fusion plasma. And the goal of part of that, of the data analysis, would be to characterize, model those patterns that are a reflection of those underlying nonlinear, in general, nonlinear interdependencies. This I already mentioned. That's another motivation. Of course, we just have large data sets, but I'm also here to say that it's a common misunderstanding that you need to have a lot of data. Well, having a lot of data is a prerequisite for doing data science. That's not the case at all. In fact, in many applications, it's exactly because you only have limited data with uncertainty that the necessity of good, solid data analysis arises. This fact that we are dealing with systems in general, be it the climate or a fusion device, systems with a lot of degrees of freedom, multiple dimensions, if you put it into a data space. And being three-dimensional beings, we are only able to look into 3 dimensions. And really, if you plot data, usually people, especially in fusion, tend to look into to diagrams plotted in 2 dimensions with 2 axes. In reality, of course, data form patterns in multiple dimensions, and to look efficiently into multiple dimensions, you need specific data analysis algorithms, and computers are also good to do that, to look at multiple data points in multiple dimensions. It's also inevitable that the sources of information, like in a fusion device, for instance, multiple diagnostics, come in many heterogeneous forms and formats. And hence, part of the data analysis has to deal with those heterogeneous sources. In fact, a lot, and most data scientists would say the majority of time spent to data analysis, and I'm sure many of you are also familiar with that, is spent on cleaning and transferring the data, and especially put it in the right format, and to be able to be processed by a specific routine. And it's only the minority of the work that goes into the real core analysis using more advanced tools from probability and machine learning. And that brings me to these broad activities in data science. Data analysis is the extraction of useful information. Also, data visualization serves to transfer from the measurement device to the scientist or the decision maker the information that is inherent in the data, but then also data archiving, data retrieval, data cleaning. That's also part of the work. The methods are from statistics, probability theory, and more recently, the words machine learning and artificial intelligence have crept into the daily usage. Of course, these fields are all very much interrelated, and I also want to say a few words about that. So just one more slide about these various data science activities. I can say that most of the time goes into these low-level activities: data cleaning, resampling, filtering, transformation. Then there are a number of intermediate, as I classify it here, data intermediate tasks like spectral analysis with Fourier transformation typically, visualization of data. Inverse problems is also often seen, although far from trivial. It's often seen as a necessary evil. So you have a number of line integrated measurements in a fusion device, for instance, from spectroscopy, and you have to invert that to get a profile, either in one radial dimension or in 2 dimensions, or even in 3 dimensions. And then at, one could say, a bit more higher level core data analysis come the methods of probabilistic and statistical inference, because we have to deal with that uncertainty that is always there. We use those methods for parameter estimation. So once you put a model on a certain, to describe a certain data set, you want to estimate usually parameters of that model. And test hypothesis, compare different models, test hypothesis of the value of certain parameters, the fact whether a measurement or the difference between 2 measurements is statistically significant or not, and so on. You want to also make predictions and then eventually take decisions, informed decisions in light of that uncertainty. Error propagation is also an important issue, not only in analyzing data from diagnostics, but increasingly also error propagation. And in this context, it's often referred as uncertainty quantification, error propagation in modeling codes, numerical codes. So how does the error from the input, for instance, a profile or a gradient on a profile, how does it propagate to the eventual quantity of interest? Pattern recognition is, like one could say, is a subfield of machine learning, or sometimes it's an alternative word for machine learning. And in pattern recognition is typically about clustering, and so finding certain regimes of or groups of measurements or data in a larger database. Then regression analysis is more of a continuous, tries to quantify more of a continuous a pattern arising because there is redundancy in the data sets. Some of the variables are interrelated, and as a result, in your high dimensional data set, you will get manifolds, submanifolds, so curved surfaces, and these you can characterize with regression analysis or manifold learning techniques and so on. And then dimensionality reduction is also an important task for visualization of data, and so projecting high dimensional data sets to lower dimensions, or also learning relations between variables. Then other tasks are more like things like event detection, for instance, advanced detection of disruptions, object recognition like dust or hotspots in a fusion device, or object tracking. And then also shape analysis, for instance, for characterizing coherent turbulent structures, or also tracking hotspots on a diverter plate. You will benefit from shape analysis. So what is data science? What is a data scientist? Well, what is on top here is domain expertise. And by domain, what is meant is the specific application domain in which the data scientist happens to be working. And usually in the lifetime of, one could say, a data scientist, or he will work in several different domains. And so fusion might be just one of the applications of some data scientists. Although at this point, in this stage at this point, one could say data science and fusion is really only at the beginning, in its infancy. Not that many groups in fusion are actually working on data science or probability or machine learning, although over the last 10 or 5 years, it has been increasing quite a lot. So the importance that is and the opportunities that are seen for data science and fusion are increasing very fast. So, but that's why I also sometimes say you have to, if you speak with a data scientist as from the perspective of a domain expert, like for instance, you are working in fusion or in finance or in climatology or geology, and you're speaking with a data scientist to try to get them to solve a certain data analysis problem, you have to show some compassion, because the person you are speaking to, the data scientist you are speaking to, is most likely not an expert in your domain. And so there's a lot of interdisciplinary interaction that has to take place. You have to convey your points and the domain expertise to that data scientist. But the data scientist automatically also gets involved into that domain expertise. So he has to learn a little bit about it. Then it's also a bit of at the crossroads of between mathematics, of course, statistics, one could say, and then also computer science, where we would situate more the topics of machine learning, data processing. And at the intersection of all these disciplines, we find actually data science. And that is another famous graph where you say that, okay, it's actually, data scientist is at somewhere at the intersection between engineering, math, and statistics, computer science, and hacking, whatever that means. And at the intersection of all these domains, you find nerds. So at the intersection of those intersections, you find the really hardcore nerds. Okay, that's of course just a caricature, but what is interesting to note also in my expertise, so we are teaching, we are Department of Applied Physics in Ghent, so we are teaching to physics engineers and physicists and astronomers, and increasingly we see that people from those physics backgrounds, like I guess most people also attending this talk in Fusion EP, have a lot of those people have some natural interest in data analysis or machine learning, not only because it's kind of a hot topic and maybe even a little over stated, a bit of a hype recently, but also because they realize, of course, that there's a lot of job opportunities in those areas. And also from the point of view of companies, there is an increasing demand for generalists, as one sometimes call these, not with too strong mathematics or too strong computer science background, but instead with a more general, sometimes pragmatic attitude towards solving complex problems. And this is exactly this pragmatic attitude, always approximating models by necessity. That is an attitude that physicists have. And so they are increasingly being asked for machine learning jobs as well. And we also see that in teaching. Okay, so now coming more to the area of applications in fusion, there's of course a lot of challenges, general challenges, and again I mention here the challenge of uncertainty. And what I mean by that is not only uncertainty in measurements and model, but also stochasticity. So if you have typically in fusion plasma, is a very stochastic medium, one could say, because a lot of the quantities in that medium are actually fluctuating a lot. And sometimes the fluctuations themselves are of interest. Like for instance, if you're studying turbulent fluctuations. But sometimes that is merely regarded as noise. Like for instance, you're not interested in the fluctuations that create the noise in the electronics of your measurement system. So some of that's interesting to note, that some of that stochasticity can be of interest and sometimes not. From the point of view of let's say, Bayesian probability, that is all the same kind of uncertainty, be it measurement uncertainty, even uncertainty because you have a certain systematic uncertainty, or stochasticity in the system because the system itself fluctuates. It's all sources of uncertainty. And to address those sources or model those sources of uncertainty, you need probabilistic or statistical inference. To model the interdependencies, causality, cluster structure, you would apply pattern recognition. High dimensionality, that is also an issue because we are dealing with a lot of variables, dimensionality reduction and data visualization. And then, of course, whether you want it or not, we have massive databases. And also for plasma control, we have to work increasingly in real time. So the constraint of having not only advanced analysis techniques, but also fast analysis techniques is important. The constraint of speed is also of importance. Okay, so we are, as I said, Department of Applied Physics at Ghent University, and since many years we have been working in an area what I call fusion data science. So data science with applications to fusion, and more recently, this has become the main focus of the research in Ghent. So what I would like to mention here as one characteristic of our work is that we try to base everything on solid mathematical foundations. On the one hand, we have Bayesian probability theory, and on the other hand, there's something that I will explain that is called information geometry that we also put to good use for our applications. You might ask, where is the machine learning? But from my point of view, machine learning is just something that is built upon probability theory. It's a bit of a simplified statement, but it's true that many machine learning algorithms can actually be derived from probability theory, and the advantage there is that in doing so, you are forced to think about the assumptions and the approximations that go into your machine learning algorithm. But it's also important to note that actually probability theory and machine learning often, and statistics often, try to solve very, very similar problems. The communities are a little bit different. And the approaches and techniques are sometimes a bit different. You will often see that basically the same techniques has multiple names in the different fields, but machine learning has been called actually a fancy new name for what is basically statistics, which is also an oversimplification, but to a certain extent it's true. Second, key point that is characteristic, I hope, for our work is transparency. We realize that we are dealing with a tremendously complex physical system. In explaining the methods which we apply, the data science methods which we apply to try to further the understanding or the control of that system, we have found that it is extremely important to well explain in a transparent way to the domain experts, so the physicists and the engineers, exactly what you are doing with the data. Because physicists and engineers by nature are very suspicious people. And I can say that because I can make fun of that because I'm a physicist myself. But and I gradually converted a bit more to data science, but very suspicious people in a good way also. So they always want to know, they don't trust what you did if they don't understand what you did. And that also forces you to think very well about what you are doing with the data and the various assumptions that go in. And hence, again, the importance of solid mathematical foundations. And that's also maybe a little bit of criticism or a bit of a caveat that I see in a new development or let's say a field that takes on the new developments in machine learning. Many people immediately run to the most fancy, complicated models like neural networks, of course, or deep learning that are out there. But it's extremely important to first start, like in what we also do as physicists. You start from a simple model. If that is sufficient, don't go to more complicated models, because you immediately run, especially in a very complex system with complex noisy data like in Fusion, you immediately run into the danger of overfitting your data and not being able to extrapolate, to generalize to new physical regimes, to new devices, and so on. So start with a simple model, and maybe only then, if that doesn't work, go to more complex models like a neural network, which is just a model with more parameters that is more flexible in learning the pattern that you're trying to learn from the data. And then finally, it's what I also try to always stress is that it's extremely important to take into account physics information in constructing a probabilistic model or machine learning solution to also in Fusion. There's even a whole subfield of physics-informed machine learning where you constrain the machine learning, like a neural network, to learn a complex model within some physical boundary conditions. Like, for instance, you could say just conservation of energy is a very simple boundary condition, but also a partial differential equation that you trust could be a boundary condition in a certain sense. And that's a bit of a field of tension, again, between physicists and data scientists, I think. And in that sense, like in astronomy, the people have already gone through that process. They are already a little bit more advanced in that. Even in the deep astrophysical journals, you can publish a purely probability theory or machine learning paper, if of course it has some influence, also some importance also to the underlying physics, which is not entirely the case in Fusion. And the reason often is because there's, again, this misunderstanding that your approach is either physics-based or data-driven. And those two, in reality, are two extremes of one continuum of approaches. So that's also very important. If there is relevant physics information about the system that you're studying, which hopefully is usually the case, then you have to try to incorporate that into your data analysis methods. Okay, so that's enough about the generalities. Let's go to some of the basic methods that, for instance, we use in Ghent for our data science analysis. Okay, so Bayesian probability theory, as the word implies, is based on Bayes' theorem, and it's deceptively simple. And I guess many of you have already seen this, because it has become quite popular also in Fusion and in more generality among physicists. This is an approach to probability theory that is somewhat different from what most people are still being taught, and I would say, unfortunately, at university and high school, which is the frequentist approach. I think for physicists, Bayesian probability is more natural in medicine and in social sciences, also in particle physics, I think frequentist methods tend to be more popular. Okay, so Bayes' theorem, what does it say? So very simple conceptually. Suppose you have measured some data, and I summarize this here in a data vector. So that is in its most simplicity, one could say it is going to be often a voltage on a sensor, like a CCD camera or a magnetic coil, or or you measure a certain magnetic flux, but eventually it's often going to translate into a voltage. But that's just one example. You measure data, raw data. But what you actually want to know about the physical system is some physical parameter which appeals to our intuition about the physics of the system. And I summarize that here by a vector theta. The vector of what you could say are the model parameters, like, for instance, the plasma current in a certain position in the plasma, so at a certain position, or the plasma density. And what is also very important in the Bayesian approach is that all the probabilities are conditional. So if I want to characterize the probability or the probability density for a continuous variable of observing the data given, assuming certain underlying properties of the system, this is how you write that. And that is called the, oh, I go too fast. That is called the likelihood. Again, it's a conditional probability of observing the data, assuming some underlying state of the physical system, which in reality you don't know. So, for instance, assuming that the plasma density in that position at that time has a certain value, what voltage would I measure, or what intensity, light intensity for a spectroscopic diagnostic would I measure? So what would X be? It's always a conditional probability. And for completeness, we also usually mention that it is always also conditional on implicit knowledge. You always know something about the system more than the assumption about the parameters. You have your model, that is additional information. You have boundary conditions of certain variables. You know, for instance, that the plasma density has to be positive. That is implicit knowledge. In the Bayesian approach, you always have to start from one step back before taking the data. And that is called what the prior distribution is about. What do I know about the model parameters? For instance, I know that the density is positive before I take the measurements. And then there is this normalization factor here, which is called evidence, which is very important if you start comparing different models. And eventually, what Bayes' theorem tells you, if you combine all these probability densities in that way, it does something almost magical because it gives you the inverse probability, the probability of exactly what you wanted to know, like the density of the plasma, given your measurements. So that's exactly what you're after, this probability distribution. Okay, and that is called the posterior distribution. Okay, that's one piece of back fundamentals that I wanted, or basics that I wanted to mention. Another piece of fundamentals is information geometry, and I will use it later in the applications, and I will make it try to make it clear by a very simple analogy. Suppose we have two measurements. So I put 2 points here in an abstract data space. And the point is often that if you zoom in, so to speak, on those measurements, you often see that they are not exact, and actually you always see that they are not exact, precise numbers, or the quantity underlying that number is not an exact number. It's a whole distribution. For instance, if you measure the density in the plasma, actually that is an average. It's an average over some kind of probability distribution. Because if you would measure the density again, you would see that at the same position at the time later, you would see as a slightly different value. And that relates again to the fluctuation of the system that I was mentioning before. So this is, for instance, a time trace of the density after a lot of processing in a jet pulse over time. So you see, of course, that it fluctuates. It's not one value. It's a whole collection of values. And if you would put exactly this signal in a histogram, then you get an estimate, let's say, of the underlying probability distribution. It looks somewhat symmetrical, and this is often, of course, the shape that we will get for probability distributions. This typically symmetrical Gaussian shape. You see that it has a certain center, a certain width, with what we could call an error bar, a measure of uncertainty, a measure of fluctuation of the system. From the Bayesian point of view, it's all the same. But this is another example. These are individual Elms, or the signature of individual Elms, measured by a beryllium-2 line in jet over time in a certain pulse during H-mode operation. And you see all these bursts of light from the edge of the plasma. But you also see that all the bursts are slightly different. It's extremely difficult, of course, to predict exactly how large the next burst will be, or for that matter, how long it will take between two individual bursts. You see that Inter-Elm time is always also slightly different from between two Elms. So what we say again, that we are looking at the quantity, for instance, the Inter-Elm time, that is fluctuating. The size of the Elms is fluctuating. Although the spectroscopic signal is not a good measure for Elm size, it does tell you that the Elms, not every Elm has the same size. There is a whole distribution, actually, of Elm properties. And again, if you would plot, for instance, the Inter-Elm time, the time between two consecutive Elms for a whole series of Elms in a histogram, you could get, for instance, something like that. In this case, you see it's not that symmetrical at all. It is clearly not a Gaussian distribution. So that's interesting. There's this additional structure in that probability distribution. It has this heavy tail. And I will come back to that application later. What I'm trying to say at this point is these two exactly precise measurements, that's an illusion. You always have underlying two probability distributions. And given that, that knowledge, a problem turns up. Because if these two measurements are exactly precise, I can measure the difference between these two measurements. And often that's going to be, and we don't think about it in that way, but actually what you're often calculating is a Euclidean distance in the underlying data space. In this case, B is the same between these 2 points, but that's the general distance. If you plot data, a cloud of data points in a multi-dimensional data space, it's always a Euclidean space with Cartesian coordinates. And it's important to realize here is that the distance between each pair of data points in that data space is the basis, is the very geometrical basis of a lot of high-level data analysis that we are going to do in that data space. For instance, you know that the whole concept of a cluster hinges on the concept of distance, because it means that the inter-point distance between a subset of the data tends to be smaller in that cluster than if you look at the distances with data points that are outside that cluster. So the whole concept of a cluster, a group of data, is based on the concept of distance. But also other patterns like a regression line or regression surface, that is actually geometry. It is again based on the concept of distance between points. And the problem that I'm trying to get at is the following. We want to take a probabilistic approach. We realize that we have uncertainty or fluctuation in the system, and we want to take a fundamentally probabilistic description of all the quantities that we measure. But then if you want to do pattern recognition, we need the concept of distance between points. But if everything that you measure is actually probability distribution, how are you going to measure the distance between two probability distributions? And that's what's indicated here. If you have a cloud of points, how are you going to say how different these two clouds are if you consider them as an entity in themselves? Now, in history, luckily, in mathematical analysis, solutions have been found to that question. And one solution that is kind of obvious, if you have a point and a cloud of data, you want to get a measure of the distance between that new measurement and that cloud of data. What you could do is this: you measure the sum of squares between this point in a certain data axis and the same quantity for the other points. In fact, something that is better is to take also the spread of the data points, and then you would divide by the standard deviation of the measurements. And in multiple dimensions, that would be like the shape of the cloud. It's characterized by the covariance. This actually has a name, and also you recognize, of course, what is inside the exponential in a Gaussian probability distribution, and that is not a coincidence. There's a very deep connection between this measure of distance. What is it's actually here. It's called the Mahalanobis distance. It has a name. That measure of distance is fundamental to the Gaussian probability distribution. And that brings me to the generalization of information geometry. And it's relatively abstract, and you might wonder at this point, what is he actually talking about? Because I thought that this was going to be a talk about data science and machine learning and fusion. But bear with me for a moment, because I will show you in the applications how it all comes together. It turns out that if you have a probability distribution with certain parameters, and parameters might be the parameters of the physical model, but from a statistical point of view, you could say that the mean and the standard deviation of a probability distribution, those are exactly the parameters of that distribution. And you can generalize that to the parameters of a physical system. But what you have is the probability distribution of the data given certain parameters. That is going to form a family of probability distribution, meaning that for every value of the parameters, you have a different member of the family. It turns out that such a family of probability distribution, like the Gaussian family, does not forms a manifold. And a manifold is the mathematical term for a multi-dimensional curved surface. and the coordinates on that manifold are exactly the parameters of the probability distribution. It then turns out at a certain quantity, what is called the Fisher information, very well known in statistics. It's basically the second derivative of the log of the likelihood of the distribution and then taking the expectation. So the curvature, let's say, of the probability distribution. Well, that quantity forms a metric tensor in those spaces of probability distributions. And people who are familiar with general relativity or differential geometry will know that if you have a metric tensor, then you can measure distances between the points. And that's what I wanted to get to. I want to measure the shortest distance between two probability distributions, or the geodesic distance. And this example will make things a bit more concrete. This is one model, an embedding, it is called, in the three-dimensional Euclidean space of the Gaussian probability distribution. So this is a surface, it looks like a trumpet. It's actually the technical name is the pseudosphere or the tractroid. It's a curved surface, and I can label it by two coordinates. And these are the parameters of the Gaussian probability distribution: the mean in the circular direction and the standard deviation in that direction that goes up. And every point on that surface represents a Gaussian probability distribution. So you see, how, for instance, this purple one has a mean of 4 and a standard deviation of 1.2. And it's drawn here on an axis, and this could be a certain physical quantity, and it has this probability distribution. And then I draw this orange one, and I did this on purpose. It has a slightly larger mean, so you see it's to the right of the purple one, but and also slightly larger standard deviation, so it's a bit wider. What I also did on purpose is to draw the cyan point and this dark purple point here, and those are these two distributions. They have the same mean, so they lie on the same tractrix, as it is called, the same curve here, and the same curve here, same mean, so they are above each other, but they are much wider. They lie at much higher standard deviation, so they are much wider. The question is now, which of the two pairs of distributions are more similar, are closer together? Well, it turns out, if you do this with our tools from information geometry, that you get the correct answer that is also intuitively clear, which is that these two distributions here are closer. Because if you think about the fact that these are not structureless points, but each of them is a probability distribution, you understand that these have to be closer because they agree more about the underlying state of information of the quantity that you are measuring. Whereas these two are much more disjunct. They don't overlap that much, and that makes them more different. So the distance here is actually larger. If you would calculate that with the Euclidean distance, you would get a different, exactly the opposite answer. And that is why that surface of probability distributions is actually curved, and the geodesics are drawn here. And again, you might, from the intuitive geometrical intuition, you might say, but why this doesn't look like the shortest curve between these 2 points? I would rather go this along a curve here. But then you have to remember, you have to recall that this is actually a symmetrical periodical model. So if you turn around once, you're not back at the same place. You're actually 2 pi further, and that's why you have these complicated shapes. What you have to remember from this rather abstract exposition is that now we are able to measure quantitatively how different 2 probability distributions are from one another. So that's extremely important. We have a new tool to quantify uncertain states of information. Okay, and that brings me to the applications. One of the oldest applications that we have been working on, indeed, I started with that application during my PhD, of course, quite a few years ago, is Bayesian modeling of fusion diagnostics. And the underlying principle is the following. It's actually all about data fusion. And of course, it's a bit different kind of fusion. It's not nuclear fusion. It's realizing that in studying that complex physical system that is the fusion plasma, we have usually multiple means. It's a bit of a luxury actually, multiple means to measure the same physical quantity. The plasmaticity can be measured for instance, on the physical principle of interferometry, or you can use other spectroscopic means like Thomson scattering. And likewise, you often have several diagnostics available that all give you some information about the same physical properties of the plasma, like the density, the temperature, the purity of the plasma, and so on. And this is that's what is also sometimes called integrated data analysis, or Bayesian integrated data analysis is all about, to exploit that redundancy in the data to improve your knowledge about the underlying physical quantities. So to make things more concrete, suppose you have diagnostic A, and it gives you a number of measurements by repeated measuring, repeated several times, a number of measurements NA of a certain physical quantity in the plasma. In reality, you don't directly measure that quantity that is represented by the unknown parameters theta A. In reality, you measure the data XA, and you have NA points in a vector XA. What is called the forward model is the model that relates the value of the underlying physical parameters, which in reality you don't know, you want to know. That forward model relates those values to what you are measuring. And we call that sometimes synthetic diagnostics. If you go really deep into the details of your diagnostics, you have a certain model that allows you to calculate, suppose the true plasma density would be that, what would I measure on my sensor, my diagnostic? And I include another quantity, and actually I should mention here that suppose that is actually the quantity that you're most interested in. So your forward model relates the quantity Q to the data about Q, but there are other additional physical parameters, like if you want to measure the density with Thomson scattering, you're going to get the temperature whether you want it or not. And other quantities, there might be atomic constants, there will be atomic constants, atomic data which you have to take from some database, but also those were measured during some experiments and have some uncertainty. So they are additional parameters in your forward model, and that is represented by this theta A. Okay, and then secondly, you have a diagnostic B, gives you again NB measurements about resulting in data XB, but it contains information through the forward model about the same physical quantity Q and other parameters of the system. What is important here is that for two different diagnostics, these two forward models are going to be quite different. They are related ideally to two completely different physical ways of measuring, like spectroscopy and a magnetic measurement, for instance. And when you have that kind of situation, you actually are often able to strike gold with that, because it is often the case that one diagnostic has a certain advantage in one way. It might have a very good temporal resolution, but it has poor spatial resolution. And diagnostic B might be the opposite. As very good, I forgot how I put it, but maybe a very good temporal resolution and very poor spatial resolution, the opposite. Well, the data fusion, for which there exist also multiple other methods, data fusion from the Bayesian point of view is this, extremely simple. You create a joint likelihood, which is the joint probability distribution of observing the data from diagnostic A and the data from the diagnostic B, given the unknown quantity Q, other parameters, uncertainties about all these data points, XA and XB, which might be standard deviations or something different. And here I did something very simple. I actually assumed that these measurements come from a Gaussian probability distribution. So the uncertainties have a Gaussian probability distribution, and they are statistically independent, which means that by the joint probability distribution is just the product of the underlying the individual probability densities from the two diagnostics. That is often a good approximation because the two diagnostics are to a certain extent independent. Well, if you recall Bayes' theorem, that is actually, this joint likelihood is let's say, one of the main ingredients together with the prior distribution of Bayes' theorem, because now you can just write down the posterior distribution, and through some technical tricks, you can get no matter how complicated that distribution, you can get information about that distribution, for instance, by sampling from that distribution using Monte Carlo methods. So the advantages are you can exploit the strength of each of the different diagnostics, but even more, you have proper error propagation. And so there is, what I mean by that is that, and this is also true for an individual, for a single diagnostic, you don't have to have multiple diagnostics for that. The uncertainty in all the parameters and all the measurements that come into that complicated physical system that is actually also that diagnostic, all these uncertainties, they propagate in a very complicated, possibly nonlinear way to the eventual quantity that you're interested in. And that error propagation, again, you don't have to do complicated calculations with Gaussian error propagation. Bayes' theorem does that for you. That is why, again, I call it something magical, I would say. And it's even possible to estimate systematic errors, but of course, you don't get something from nothing. Estimating systematic errors has to come from some information. Maybe you have some extra diagnostic that contains exactly that little piece of information that allows you to constrain a certain systematic error. But you can just model a systematic error by an additional parameter and treat that parameter as an additional parameter in your grand probabilistic model, and then make estimates about that parameter. This is an illustration used by tomography. And at first sight, you might say, what on earth does that have to do with what you have just been saying? Because exactly what is the forward model here? And what is the data? What is the underlying quantity that I'm interested in? Well, it's exactly what is written here below. What you measure are the line integrals. You look into the plasma, for instance, with spectroscopic diagnostic, and you see all the lines along these line integrals. But what you're interested really in is in the profile of a certain quantity. Here is the soft X-ray emissivity inside the plasma. So you go from here, these time traces of line integrals, to here. That's what you would like to do. But that is actually the inverse problem. The forward problem is assuming a certain emissivity in each pixel, you could say, in that cross section, and going to the measurement. That is the forward model. Now, it's often called, people often speak about tomographic inversion, because that is what analytically you're actually doing. You're inverting the system, the forward model. But actually, from the Bayesian point of view, it's not really an inversion. The inversion is done again by Bayes' theorem. Going from the forward model to the inverse model, that is exactly what Bayes' theorem does for you. You want to know the probability distribution of the emissivity in each point in the plasma or along a certain radial coordinate given the measurements. And what we did in this particular application is to model each of the pixels in the cross-section. You just divide the cross-section into a number of pixels. You model the emissivity over time, because you're going to get a signal, it fluctuates, or it might go up systematically or go down. If, for instance, an impurity comes into the plasma, you model that signal by a Gaussian probability distribution. And then you do that for all the other pixels. And since, in fact, yeah, okay, a pixelization is a discretization of the system, but in reality, you have a field, a whole field. What you actually get is what is sometimes called a Gaussian process. And a Gaussian process can also be in one dimension, but here it's in 2 dimensions. You get an infinity of Gaussian probability distributions. And from what it means is actually that you have one big joint Gaussian probability distribution of all the emissivities in all the pixels. And the second ingredient here is that you impose a certain correlation of the probability distribution between neighboring pixels. And that is important, because if you would not impose that, you would just get one noisy profile back, because you allow too much freedom. By imposing a certain correlation, a certain strength of correlation between neighboring pixels, you are actually saying that if the emissivity goes up in one pixel, then most likely, when the correlation is large, the emissivity in the neighboring pixel is also going to go up. So you have that correlation. And that is the basis for the structure that you are seeing. Correlation in the probability distribution gives you that structure and not a random noise. The additional advantage of this approach is that you get the Gaussian process back as a posterior distribution. So it's extremely fast. You can actually do this tomography in real time. And an additional advantage, and that is of course inherent to a probabilistic approach, is that you get a certain measure of uncertainty. And here that gives you you can say the posterior variance. And for inverting this shape, for instance, you see that there is most of the uncertainty is here in the center. For this more asymmetrical it's a synthetic emissivity profile. This is the original. This is the reconstruction. You see that is quite good, but you see that the largest uncertainty is also here in these 2 lobes. Then you can start to investigate more, and you can even do some kind of diagnostic design, because you could ask the question, where do I have to put the next line of sight or the next measurement in order to minimize the uncertainty on my inverted profile? That is called Bayesian experimental design, but I'm not going to go into that. Okay, so Bayesian modeling of fusion diagnostics. I now come to another application that we have been working on quite a bit, scaling laws. You have heard about that, even if you're not involved into scaling laws in fusion, you probably have heard about it. A lot of quantities, we are interested in how they depend, what their parametric dependencies are. And the ubiquitous example is the confinement time in H mode or in another regime. How does that, the global confinement of the plasma, how does that depend on certain other characteristic of the plasma? Because that is important to design new machines or to understand what influences the H mode confinement. And that is so complicated that physicists are still trying to understand from first principles, and it's extremely difficult due to the turbulent transport. Still trying to understand from first principles how the confinement is really related to the basic properties of the plasma, like the plasma current, the plasma density, the power going through the separatrix, and so on. And it occurs a lot in fusion. All these empirical scaling laws. It's called the scaling law because it basically tells you how a certain quantity scales from one situation to another, or from one device to another. What happens with the confinement if I change the magnetic field to the one in jet, from the one in jet to the one in ITER? Well, the scaling law is a convenient means to tell you that. It's actually just an application of regression analysis. So people in fusion call it scaling, also because there's a history of self-similarity of scaling laws, but I'm not going to go into that. And that's why a power law, a monomial or a power law, is often used, but it's really only one model. In reality, in more generality, it's just regression analysis. But you might say it's all regression analysis, what's fancy in that? But there's a lot of issues to be addressed. You have uncertainties in all the variables, whereas usually regression analysis only takes into account the uncertainty in the response variable, like, for instance, the confinement time. Heterogeneous data from different diagnostics, heterogeneous error bars, collinearities, correlations between predictor variables, outliers, very complicated underlying probability distributions, uncertainty in the model, because people put a power law on that as a model, but that's often just a hunch. It could be much more. Nobody tells you that a power law is the best model there. So that has motivated us to look beyond the most simple regression techniques, which is least squares or weighted least squares. We are using Bayesian regression analysis, robust methods to estimate that. A method that we have invented ourselves, geodesic least squares regression, very robust also and very simple. That's the advantage. Or non-parametric models like Gaussian processes, neural networks, and so on. Surrogate modeling, and so that's also becoming very popular in fusion. You have a certain modeling code, but it takes a lot of time to run. Well, you can model, if you have a lot of runs, you can map, you can teach a neural network or another model to learn the mapping from the basic input of your modeling codes to the output. That is called surrogate modeling. And if you do that well, then you can run your, so to speak, your modeling code in real time, in the control room, or between shots, or even for plasma control. And that's where we're really moving to that kind of numerical modeling being transferred from large supercomputers eventually to real-time control. By the way, how much time do I have actually?
You're not that restricted with your time, so it's mostly up to you.
Okay, yeah. So that gives me another 2 hours then. No, I'm kidding. I think like 15 minutes, 15 minutes and a quarter of an hour, and then I try to finish. So just for people who are not really familiar with scaling laws, maybe you know that this is the form of the confinement scaling. So this is the global energy confinement time, and it depends on a number of plasma parameters. Through this power law. This is called a power law, always to the power of something. And these are the parameters that you want to estimate. So basically, it's just a regression model. You have some data, and you have a number of parameters in the model, and those are the ones that you want to estimate. I also include here the triangularity, because this is, we are working on, within the ITPA on a revision of the H-mode confinement, because this is already 20 years old, and it's high time to do a revision. Okay, and so we include also triangularity. I'm going to skip a little bit because it's relatively technical. What I want to say here, so don't look at the equations here at the bottom. What I want to say here is that classical regression analysis only takes into account, maybe some of you don't know that, but classical regression analysis only takes into account uncertainty on the response variable. It acknowledges that you are measuring the confinement time with a certain error bar, uncertainty. But it assumes that all of the predictor variables, as we call them, are measured exactly. These are exact numbers. And of course, in reality, it might be a good approximation for things like the plasma current or the magnetic field. We know this with up to a few %. But for instance, the power, and notably, the power passing through the separatrix is not, the loss power is not known to, is also has actually an uncertainty that is about of the same order of magnitude, like 20% or something, as the confinement time itself. And then you have to use more powerful methods than just simple least squares. So what my point here, I guess, is also that even for such a simple task as estimating a scaling law, or deceptively simple task, you have to think carefully about the fundamentals, what kind of methods you are going to use. And maybe as an additional message here, take-home message, is that this is actually an example of something hybrid between, it's a simple example, but it is nevertheless an example of something hybrid between physics knowledge, physics understanding, and a data-driven approach. Because the variables, the predictor variables that occur in this scaling have been selected with physical knowledge about the system in mind. And then you use an estimation technique, like for instance, in the simplest case, least squares, to estimate the parameters. So it's very simple, but it is an interesting example of the collaboration between the physicists and the data scientists. Okay. In reality, I say a deceptively simple problem, because in reality it's much more complicated than that. And one of the other reasons, apart from uncertainty on the predictor variables, is that these measurements come if you put them in a database from many different machines, these measurements are of a very heterogeneous nature, from different diagnostic, different error bars. So you have you don't have a very nice regression surface in that multidimensional data space. You have a very messy structure of the data. And given that, you have to try to fit an extremely simple model to that complicated data. Here you recognize, of course, the Gaussian probability distribution. This is just another way, it's called maximum likelihood in a simple sense. It's just another way of writing least squares, but you take into account also the uncertainty on the measurements. So actually what I'm doing here is to estimate the parameters here, the exponents here, which I put in this eta. I call eta the log of the confinement time, according to this model. So you have to imagine that here eta is what my model tells me that the confinement time is going to be. In reality, I measure a certain experimental confinement time, which I call y here. And what least squares does is to minimize the sum of squares of these differences between what the model tells you and what the data tell you. And the hope is that that will eventually allow you to estimate the parameters. What maximum likelihood, or also Bayesian regression, does is to maximize this sum of product, let's say, of Gaussian probability distributions, Gaussian likelihoods. And you immediately see that it is actually more or less the same. If I maximize this distribution and I take the product here of over all the individual measurements, in reality you have a cloud of measurements from different machines, so I take also the product of each of the different tokamaks that provide data into that database. So I assume that those probability distributions are independent, so I can take a whole big product. But actually, if I maximize that product, you see, due to the minus sign here, it's equivalent to minimizing the sum of squares. Except that I also take into account the uncertainty. And so that is the added value of doing maximum likelihood estimation or maximum a posteriori or a full Bayesian analysis. It takes into account also the uncertainty on the data. Or in the more generality, the whole probability distribution of the data. What we did also is to include this little fellow here, this gamma k, and that is just an extra factor, and I don't know what that factor is a priori before taking the measurements, but it is supposed to model additional uncertainty. I acknowledge that in reality, I don't know exactly what the uncertainty is. I have some measurement uncertainty eventually coming from the diagnostics, but in reality, the spread of the data around that regression surface has a very complicated distribution. And to be fair, you have to admit that you don't know that distribution. And that factor gamma, that is its function. It's a very simple way of saying, well, it's this uncertainty, but it could be also a certain multiple of that uncertainty. And those factors gamma, if it's a systematic uncertainty, if you will, are going to be estimated. It turns out that it's possible to estimate them if you take enough data. And I can also estimate these quantities here. And it also turns out that that trick makes your regression method, your estimation method, very robust. What I mean by robust is robust against all kinds of uncertainty in the data, in certain uncertainty also on the model, because that power law has certain motivations, but it's actually, and it's also more recently become clear that it's actually deficient, that model, in several respects, and people have been using more complicated models. This is a bit a different approach. We acknowledge, we still use that power law model, but we acknowledge that there is uncertainty in that model, and we want to take that uncertainty into account. Okay, another cartoon maybe that will make things a bit more clear. If you do least squares, this is actually, so this cartoon, so you have a number of, a quantity y, that is the response, like the confinement time, and it depends on a certain quantity x, like the plasma current. And the relation is more or less linear, and you want to estimate that line, or in more generality, it's going to be a multidimensional regression surface. But least squares, ordinary least squares does is to measure the distance, the difference, but it's actually a Euclidean distance between the measurements and what the model tells you. And you're going to minimize all those little distances. And now I make the jump to what I had been saying before about information geometry. In reality, we acknowledge that this is not an infinitely precise measurement about the confinement time. It's a whole distribution. And actually also what your model tells you is not infinitely precise. It's also a whole distribution. And this cartoon, because it's difficult to draw, this cartoon is meant to convey the message that actually the generalization from least squares to what is sometimes called minimum distance estimation is to minimize the distances between all these individual probability distributions along that regression line. So you measure, so to speak, a sum of square distance between those probability distribution. Turns out that that geodesic distance that I mentioned before is a very convenient way, and sometimes you can do that very fast also, to minimize those distances between those probability distributions of, once again, distribution that you measure and the distribution that you predict according to your model, distribution of the confinement time. So that's in a mathematical way how you can write that. You measure the distance between the probability distribution of the confinement time that you would expect if all your assumptions about the model would be correct, like it is a power law, the measurement uncertainties are Gaussian and all that kind of thing, and what in reality the data tell you. And this brings me to yet, apart from the robust Bayesian method, which I mentioned before, and the least squares, which I also mentioned, that brings me to yet another regression method, is called geodesic least squares. And this is the method that we have developed in Ghent, and which we are also using for confinement time prediction. Okay, as far as the H-mode scaling is concerned, well, these are the individual dependence of confinement on the plasma current and so on that we show. I show this here because you get some appreciation for how much uncertainty there is in some of those databases. So it's really sometimes extreme, and it's extremely important to take into account that measurement uncertainty. I'm going to skip this because I don't have more time. This here, okay, I'm going to skip also this, but I'm going to just focus your attention again on this plot here of the Elm bursts, which I mentioned earlier. Suppose that the quantity that I'm interested in is the Inter-Elm time. And I know that it has a certain probability distribution. Well, it turns out that that distribution can be rather of a rich structure, not only this heavy-tailed form, not only the Gaussian form, but also sometimes what we call a multimodal distribution, 2 peaks of the Inter-Elm time. And again, the question is, from one plasma pulse to another, change a little bit the plasma conditions. How is the distribution of the Inter-Elm time going to change? Or how is the distribution of the certain fluctuations, turbulent fluctuations, how is that distribution going to change from one regime to another, or from one plasma condition to another? And I don't want just a qualitative difference. I want a quantitative estimate of how different those distributions are. And you already probably feel what's coming. Again, I can put to good use my mathematical framework of distance estimation between distributions in order to systematically quantify how probability distributions of Elms or turbulent fluctuations are changing the plasma conditions. Let me just show you this. Here in the center, you see a plot of the average Elm frequency in a series of jet pulses when during a scan of let's say the input power. So you increase the power, we are everywhere in H mode, but here we are at a very low power, just above the LH threshold for this particular plasma. And what we expect and what we also see are very small elms. They are called sometimes type 3 elms. Well, if I measure the inter-elm time between a series of elms, of these type 3 elms, and I plot again the histogram, you would see that you get something that has a rather heavy tail here, as we call it. So it's a skewed probability distribution. If I as I start increasing the power, the frequency of those type 3 elms decreases. That is by definition what that makes them type 3 elms. But if I go higher and higher in input power, suddenly the frequency starts to increase again. And that is a telltale sign that you are seeing type 1 elms, bigger elms. Now, it turns out that, for instance, in JET with the ether-like wall, it's not as easy to make the distinction between type 1 or small elms more generally and the larger elms. So sometimes there is a certain overlap in size, an overlap in frequency, and it turns out that the shape of the probability distribution of the inter-elm time gives you some extra information about what kind of elms you are looking at. And so that is the application of this particular application. We want to see if we can quantitatively say how the distribution is changing if you move from type 3 to type 1 elms, for instance. And then you can plot that in also again on in a family of probability distributions. The model that I use here is called the Weibull distribution, and it has 2 parameters. So every point in this plot here is one series of elms. And then you see that the type 1 elms are mostly located in this area of in reality, it's a curved surface, this area, and the type 3 elms or the compound elms more in this area. And you can try to discriminate between that. So it's a whole new way of looking upon that problem. And maybe one more thing that I want to also mention, if you have this kind of probability distribution of the inter-elm time, you might have a problem, because it turns out that the inter-elm time is very much related to the size of consecutive elms. That means that if the time between 2 consecutive elms is long, it is quite likely that the next elm is also going to be a big one. And so the point is that the shape of the probability distribution is an extremely important ingredient here, because whereas on average, the average elm frequency, the average elm size might be below a certain safety threshold, if you have this kind of distribution, then you know that sooner or later you will get a long inter-elm time. That means likely a big elm. And trying to reduce that tail of the elm energy, that is also something that we have to strive for. So not only looking at the average quantity, but also the probability distribution. And finally, on top of my earlier statement that many, if not most, machine learning algorithms can be deduced from Bayesian probabilistic considerations. On top of that, I want to show you an application of also machine learning techniques, and that is called anomaly detection for predictive maintenance. Again, I skipped the text and I show you just this. If you are running a fusion device, and especially in a reactor, you want it to run with as few malfunctions as possible. Malfunction means downtime. You lose experimental time, or worse, in the reactor, you use you increase the cost of electricity, because the machine has a certain downtime. It has to, something has to be repaired. You have to restart the plasma and so on. That means no electricity during that time. That means you increase the cost of electricity. The most basic way of addressing failures in your engineering system, in your fusion device, or in industry, in your production line, is to do reactive maintenance. It's very simple. So in terms of complexity, it's here, but it's also not very useful, because it means run until failure. You run the device and you just see, oh, something failed and you have to repair it. That's, I hope nobody from JET is listening, but that's often, unfortunately, what is still being done in many devices, and not only JET, of course, but JET is a bit vulnerable because it's in the spotlights, and it's also becoming a bit old, and many subsystems are breaking down, but it also happens in other devices. And often, unfortunately, that's what happens. You run the machine, something breaks, and then you have to send everybody home. A bit better is preventive maintenance, what people also do to a certain extent already since a long time. You do some planned maintenance. You realize that you know that after a certain time, a pump or a certain switch or whatever is going to wear, and it's going to fail. And so you plan and you schedule a certain repair time. After a few months, or like a month or a day, you shut down the system and you do repair. The downside is that also might increase the downtime of your system, and maybe it wasn't necessary because the switch or the pump or the system was still functioning fine. So there comes in predictive maintenance, and sometimes called in part of Industry 4.0, big data, Internet of Things. If you throw in your PowerPoint a lot of that kind of buzzwords, then you have the attention of managers. And but there's another advantage, because what it is about is you teach a computer to recognize first to monitor using diagnostics and then all kinds of sensor, temperature sensor, voltage sensor, vibration sensor. You teach it to recognize when something is probably going to fail. First to recognize signs of failures, and then hopefully also to teach it, to train it, like in neural network training, to train it to predict when the system is going to fail. And then, of course, that is very valuable information. That is called predictive maintenance. And we are starting to do that for, oh, by the way, one example of predictive maintenance that is already, where people are using a lot of machine learning already, is for disruption prediction. It's not called that way, but it's actually quite similar. You monitor the system and you try to see in the signals when something is going to break, when the disruption is going to happen. Of course, this is on a completely different time scale. This is for the jet turbo pumps. And you see that sometimes they fail. It's not always clear why. And it can be very violent, because these pumps are, this is like a jet engine. Instead of, it doesn't fly, it sucks. And so it rotates at 500 revolutions per second. And then usually if you switch it off, it should spin down in like, freely spin down in like half an hour. When something fails, the bearing breaks, then that might happen in like 2 seconds. So from 500 to 0 revolutions per second in 2 seconds, you can imagine that is not very good for the pump. And it completely almost explodes, and it breaks the pump, it creates downtime and so on. So hence this simple application where you monitor in this case, we were a bit limited in the sensor information which we had because it was built in by the manufacturer. The rotation frequency of the pump, the temperature of the bearing and the body, the voltage and the current and the power that it consumes, pressure measurements, and that is the information which we have. And these are some of the plots. And this is hours here on the horizontal axis, so different time scale than disruption prediction. So it's several weeks of operation. Of course, you have to zoom in then, but you see that the temperature varies a bit. This must have been somewhere in summer because it goes up to over 30 degrees. And you also see sometimes these peaks, these are actually plasma pulses. And if you zoom in, you would see even more. But what happens is that if a pulse, so these pumps are obviously working continuously, but if a pulse happens, a discharge, then gas is let into the vacuum chamber, and that has to be sucked out again. Then the pumps work more strongly, have to work more, and so the power consumption goes up. So you also have to teach your machine learning system not to trip over that kind of what would lead to a false positive. That it wouldn't say, okay, normal pump operation is something like that. Oh, something happens, so I have the pump has to be repaired. But no, it's just normal operation. This is a plasma pulse. You have to take that into account. But this, in contrast, is not normal. It suddenly switches off and stops rotating. What we did is, apart from another more simple approach, because remember, you always have to start from a simple model, we also trained a simple neural network, which is called an autoencoder for anomaly detection. And I'm not going to mention the details here, but basically what you do is you gather these signals, you compress them, and that is called the code, to a lower dimensionality, and then you ask the network to reconstruct the input, and you compare input and output. And the anomaly, if normal operation goes on, then you know that the output is probably going to be a good approximation of the input, because that is how you train the system. But if an anomaly occurs, like for instance, the pump shuts down, then the network is going to be a very hard time to reconstruct the input. And then you recognize that you have an anomaly. And this kind of anomaly indicator you can then plot against time. You see indeed that over time, as the pump is operating, suddenly it goes above a certain arbitrary threshold. But if that happens for a sufficiently long time, then you might think that perhaps it's time to service the pump or to look what's happening there. We also have done this in the meantime for switches for the main solenoid in jet, which is also an important reason for downtime at jet. So to be able to recognize when the switch is going to fail. And of course, it has tremendous applications, and I'm sure this is going to be one very hot topic in Fusion in years to come, especially when we're moving towards ITER, towards eventually demo, which has to run in a as much as possible, especially demo and reactors, and as much as possible quiet state, always the same plasma state, nothing's fancy. And then of course also all the other subsystems have to work along, and you have to be able to predict when something is going to fail. Okay, that brings me to my conclusion. So I think I made clear that, of course, there is a very broad range of applications of Fusion data analysis on many different levels in Fusion. So important, I think, is a consistent treatment of uncertainties. So I tried to sketch the broad lines here. And what we try to from that uncertain data, we try to extract patterns in a complex, multidimensional data space. And what is also important, take-home message, I think, is that we want to combine physical insight with data science methods. Physics-based, data-driven, it's actually two sides of the same coin. Important also, I think, if you want to do something in machine learning or probability in whatever application field, my recommendation is to start from a simple model which you understand to a more complex, more black box model if needed. And of course, this can contribute in fusion to physical understanding, also to experimental design, and a simple example is a scaling law, and then eventually also to plasma control. As an outlook, I would say that, again, we are still in the infancy of this field. All the procedures and methods have to be adopted to a much larger extent. Standardized software and tools are needed, and we are trying to, although we are quite a small group at this point, we're trying to also work towards that goal, because people are never going to adopt those methods if they have to learn a thick book about statistical machine learning methods. They want to use those methods. So we have to provide software tools. Some applications at Ghent that we think we are going to increasingly look into is more experimental design. So how to run a fusion device, which diagnostics to use, how to design new devices and diagnostics. Survival time of material components. That is also a very important topic, I think, where probability theory can make an important contribution. And then what I also mentioned before, uncertainty quantification in computer codes. So error propagation, basically. And finally, I want to mention my contact details, not in the least, because by, I hope, May or June, we are going to be in the position to publish probably at least one to start with, but then probably also two, and in the longer run, more open positions for a PhD. So if you're interested, I recommend to keep an eye on our website, which is here, in the coming months. And now you see that I'm also including a lot of uncertainty on my estimate of the time needed for my talk, because again, I'm afraid I overrun a little bit. But I thank you very much for your attention. And of course, I'm now open for any additional questions you might have.
Thank you very much for the very interesting talk on such a challenging topic. Now the floor is open for questions. Please raise your hand. There's an option in Zoom to raise your hand if you want to ask a question. And after that, please lower your hand. And if you have troubles with this option, you're welcome to type your questions in the chat. And I would like to remind you that there are no simple questions. We appreciate all kinds of discussions, and do not hesitate to ask everything which is not clear for you. Okay, I see there is one more. Mao, please go ahead.
I just want to ask about where can we get those data for training? Because I see you just mentioned, I don't know where your data come from.
Mm-hmm. Okay, the data, of course, come from various different devices. There are a number of, I could say, public databases in Fusion, and these are traditionally the ITPA databases. They used to be accessible online, but I think this is going to be transferred to Ether. So these are some of the databases that we have been using data from over the years, or analyzing data or benchmarking techniques. Then there are, as far as Eurofusion are concerned, in Europe, there is a big initiative on constructing standard databases. As far as I'm aware, there is an initiative for global confinement, for pedestal data, and also for disruptions, I think, and possibly also for other areas of the plasma physics. And these possibly, I haven't checked lately, but are also available through the user's website, the internal website of Eurofusion. Other than that, of course, it's a question of getting into contact with the domain experts, as I have called them, the physicists themselves, and to always, of course, try to explain exactly what is the goal of the analysis, and then who knows, people are going to be ready to share data with you.
Okay, thanks, Prof.
So there is one more question, the first one, which we couldn't hear, unfortunately, which is, which programming language is recommended for a beginner to start?
A beginner. Well, in data science, perhaps you know that there are basically two languages that are almost exclusively used, which is R, very much used in social sciences and in medicine. And then there is Python, of course. I must say that everything I do, I do in MATLAB. And I think MATLAB is extremely well suited also nowadays, also for data science, because there's really, if you have the toolboxes, because there are extra toolboxes there, there's really a lot of data science methods in there, and there's also a whole community behind it, and it is actually also to a certain extent open source. And the graphics system is very good for MATLAB. Other than that, I know that indeed the problem of MATLAB is the license. I'm just used to working with MATLAB, but the problem is the license that is quite expensive. And for that reason, many people are moving to Python. So that for a beginner, I would say, given the fact that so many people are working in Python, there are so many toolboxes, scientific toolboxes, and statistical and machine learning toolboxes also from the big companies like Google and Microsoft, for all written in Python. I think that is probably the best way to go. But okay, takes a certain kind of investment, of course, time investment to learn that.
Okay, maybe I will give everyone a moment to think about more questions. And so far, I would like to tell you that there is a feedback form about the talk, and I hope it will help our organization to improve. So please, if you wouldn't mind to take a couple of minutes and fill the survey that I have just shared in the chat, that would help us a lot. Okay. There is another question from Nilormi. Thank you, Professor. I'm doing a hands-on in Python these days, and how can I carry out such simulations by myself? Is there any tutorial?
A tutorial for exactly machine learning in general, or with applications in Fusion?
It's not mentioned in the question, unfortunately, but let's say about machine learning in general to start with. Application in Fusion. Oh, I've got a comment.
Yeah, well, for fusion, in fact, there is a good overview article, I would say, by, and now maybe I have to type it in the chat as well. If I can find it. So the name is, and people from IPP Garching will know this person probably. So so he's he has an overview article. I think it's in computational physics of computation, something like that, about Bayesian probability theory with specific applications in fusion. There is also a book, a very good book by the same author and two more co-authors, Bayesian probability theory for physicists, geared towards physicists, I would say, with some applications in fusion. It's not exclusively fusion, but there are some applications. Then many other people, I think, will know the name of this gentleman, Otto Cardaan, at IPP Garching has a book quite comprehensive about frequentist statistical methods geared towards basic statistical analysis of fusion data sets. And okay, with a lot of applications to scaling laws and so on. There is, as far as the machine learning is concerned, from the top of my head, I cannot really think about something that is really tutorial style. So there you're probably going to have to look more through the literature, the technical literature. But of course, for machine learning in general, there is so many tutorials all over the web. Maybe I forgot to say that Anaconda is an installation of a scientific Python that is yeah, also very much geared towards physics, engineering, scientific computing, and machine learning probability. Anaconda is a good installation. They also have a lot of tutorials available.
Fine. There is one more question from Dmitry Panfilov. Please go ahead.
Yeah, I think I can see it. So articles related to Thomson scattering and machine learning. Maybe profile fitting. So there's of course, historically people have used mostly splines or something like modified hyperbolic tangent or something to fit profiles. More recently, more flexible methods, I would say, are being used to fit profiles. And again, Gaussian processes have been used there quite a lot. There's a group at Eindhoven who is who have been using both surrogate modeling for neural networks, but also Gaussian process modeling of profiles. And I don't know exactly what from TJ2 you're referring to, but profile fitting is certainly one important, yeah, it's sort of low level, you could say, in the sense, not in a negative way, but in the sense that it's everybody needs it, and it's many people think that it is easy, but again, that's it's deceptively easy, and it's again also important to use the right methods to do that profile fitting to make it robust, and also to have error bars on the profile.
Thank you very much. I don't see any other raised hands, so maybe I will ask my question. Is there any restriction on the input data that is used for machine learning, or it can be just anything? What kind of data is used?
Yeah, I would say it can be anything. Eh? So like in statistics, you don't, I think mainly in physics-oriented science, we are of course mainly used to working with continuous variables, but in not exclusively. So we also, for instance, have been using what is called categorical data. So that means that you have data variables that take on specific discrete values, like confinement regime, or which tokamak does this data come from. So this kind of data are also important, categorical data. So as far as no, there is no limit, I would say, what kind of data you can use. The only caveat again that I would like to mention is that fusion data, because fusion plasma is such a complex physical system, there is the interaction with the engineering components also and so on. The data tend to be very complicated, very often noisy. It's very difficult to find the patterns that you're interested in, very strange distributions with outliers and so on that need a lot of cleaning or a robust method to do the estimation. But there goes a lot of thinking into that. So don't also, that's maybe another recommendation, don't feel offended. It's normal if sometimes people from the physics community think, oh, machine learning, it's all very easy. You just download a toolbox and you run the code. Well, that is the poor man's way of doing machine learning or probability. It takes a lot of thinking and hard work. And on top of that, you need the domain knowledge. So it's not an easy endeavor at all.
Yeah, that's kind of not a question, but a thought that I had, how to find a balance between machine learning and physics itself, which might not be very easy.
Yeah, I see a question about information about stochastic analysis. I think you can look into the classical literature about the statistical approach to turbulence, turbulence modeling. Although I'm not that familiar with that literature in fusion, but I know it's there. Really, to tell you the truth, despite that it might sound a bit unbelievable, but this kind of questions, and despite the fact that a fusion system is one ubiquitous example of one prime example of a stochastic system, many of those questions about probabilistic modeling of stochasticity in a fusion plasma are only now or very recently or have not been addressed yet. Yeah, I'm afraid I cannot point you to that much literature. You can have a look at some of the references that are on our webpage and bibliography, but other than that, the literature is rather scarce. Of course, I hope it's going to change towards the future.
Okay, thank you very much. Any other questions?
Just a second, Geert.
Oh,
just
okay.
a second. We would also like to know a certain story that you would want to quote about how you have seen, for example, this field progress in the in the use of Fusion, let's say, or some anecdote that you remember and that in a way helped you continue your way working for Fusion. If you could share something like that with us, that also would be a great help for us.
Okay, that's an interesting question. When I was working on my PhD, I started talking to some people who at that time were working on neural networks. And the funny thing is that that was still the previous generation, let's say, of what is sometimes now called shallow neural networks. And they had done some work on JET and got me really interested. So that's perhaps another interesting lesson I learned, unfortunately a little bit the hard way, is that it's really recommended, as with many things you learn, of course, to have somebody in the neighborhood who can teach you. If you have to learn everything from books or articles or tutorials or whatever, then sometimes it's going to be a heavy lesson. It's going to be quite a, not only a steep learning curve, but you probably most likely are going to repeat a lot of work that people first have already done, maybe in some other field, but which you could use also in your particular application, or you're going to often not be aware of an that's a same aspect of another aspect of the same problem. You're not going to be aware that certain useful methods exist out there because you simply don't know them. And if you would know somebody, ideally, of course, if you're working on a PhD, it would be your PhD supervisor or co-supervisor. If you would know somebody who has working knowledge in that field of data science and machine learning, and preferably with application to Fusion, then of course it's an invaluable advantage. And I'm afraid it's a bit the difficulty in every kind of interdisciplinary work, and that is of course part of the whole challenge. If you do interdisciplinary work, you are often going to need expertise by looking somewhere outside your immediate circle of colleagues. And yeah, so that's an important lesson which I learned by a little bit struggling along, that there is always that danger that you're going to repeat work that has been done before, or that you don't have sufficient working knowledge to use the correct methods. You run the risk that you're always going to, at least in the beginning, be a little bit of an amateur. On the other hand, the field is so new in Fusion that even if you're an amateur in data science, you're probably still going to do something new in Fusion with application in Fusion. Okay, so it has upsides and downsides. That's an important lesson. It pays a lot, and I would also say don't be afraid to ask experts in what you could call Fusion data science to ask advice about a certain application. Of course, if it's very general, then it's sometimes difficult to give advice. But if it's a very specific problem, then it pays a lot to ask advice, even if you don't know the expert, the person personally. It pays a lot to ask that advice, because otherwise, well, it might be a very difficult journey.
All right. Thanks a lot for the pearls of wisdom. I'm pretty sure this will be helpful for many aspirants who would like to not only join but make a career out of such interdisciplinary works. I give the mic back to Katya.
Last chance. I don't see any so far. Well, anyway, this talk will be, it is recorded and it will be posted on our YouTube channel soon. So if you will have more questions later on, you can comment on YouTube, or you can contact us on Facebook page. Thank you very much for your talk again. It was a very interesting topic. I've learned a lot.
Yeah, thank you very much. Thank you everyone for joining, and of course stay safe, and hope to see you at another occasion live in the future.
Thank you everyone. Have a nice evening.